Okay, I think it's 11 o'clock, so we can start. So welcome everybody to this Stardust webinar on the insights about assessing urban heat sources for use in district heating. So this is a webinar, a part of the Stardust project, Smart Cities project that started in 2017 and is about to finish in March. And so the Stardust is a smart cities project that covers mobility, ICT, smart buildings and districts, and energy. And the webinar we've got today probably spans a lot of those subjects, especially the smart districts and the energy side of things. So today I'm pleased to welcome Rossana Paradiso from EURAC Research based in Trento. So welcome to you and thanks for agreeing to share your insights this morning. You hold a master's degree in energy engineering and a master in energy management. So you work as a researcher at EURAC Research, and you've been involved in various EU-funded projects. And so today you'll be looking at how to assess waste heat sources in urban areas in terms of recovering this heat for low temperature district heating networks. Okay, the floor is, well, just before I hand you the floor, just to tell people the format. So we'll have questions and answers at the end, but feel free to use the chat box that I will have a look at as Rossana is giving her webinar. And you know, if I feel that it's a good idea to interrupt her to ask a particular question, I will, but we can have questions and discussions at the end. Okay, Rossana, over to you.
Okay, good morning, everybody. Thank you, Mark, for the presentation. As you said, I work as a researcher at EURAC, and yeah, Stardust is one of the EU projects in which I was involved, and regarding waste heat recovery from manufacturing activities and tertiary sector buildings, because in urban areas there are great opportunities for the integration of waste heat in district heating. And today we are going to focus on Madonna Bianca district in Trento, which was one of the area object of the study in Stardust. So the famous towers of Madonna Bianca are part of a complex of residential buildings built in the 70s, and in the Stardust project, they concentrated on, the study was concentrating on 3 of these towers, the study was going to they wanted to study the tower for renovate in the vision of the near zero energy buildings. So it was there was study the application of photovoltaic facades, the connection to geothermal probes for the building of a district scale water loop, in which rejecting the waste heat from supermarkets and swimming pool close to the towers. So today I'm gonna focus on our work for this project, and it was the techno-economic feasibility study for recovery the waste heat deriving from the activities close to the towers, like the shopping malls and the leisure center and so on. But before going to that, the waste heat potential evaluation was needed. So the first step were just mapping the activities, then going into a short literature review, then filtering the list of activities in order to just focus on the highest potential, and then contacting the companies in order to get from facility managers and so on real data of energy consumption, and from that starting with the calculation. Where data were not available, we made some hypotheses. So the first step was the mapping of the activity. We basically used Google Maps just to have a look on which activities were in the area. We concentrated on a 2 kilometer radius area around the towers. Just because 2 kilometers is a tentative value and since the distance is a parameter that affects actually the economic figures, we just started with 2 kilometers as a tentative value. And then we also contacted the Chamber of Commerce of the province of Trento in order to get some more detailed information about the activities in the area. We detected the most present sectors in the area, and we discovered that in that area there were shopping malls and supermarkets, but also wine production sites, fruit and vegetable transformation manufacturing, and this leisure center with swimming pools. So through the literature review, through environmental statements and best available techniques, reference documents of the European Union, we could study the processes and the primary energy uses within the companies. So which are the most energy consuming processes, and which type of energy is the most used, like thermal energy, the temperatures, and maybe electricity for cooling and refrigeration. After that, we made a filtering of within the initial list of companies. We detected initially 40 companies, but then we concentrated on 10 companies because of the distance from the towers, the number of employees, and the surface areas. These two are two parameters that directly affects also the energy consumptions, and then the possibility to waste heat recovery. And then we selected just a more energy consuming type of manufacturing or tertiary sector activity. So that from the initial 40 companies list, we detected 10 companies, but we get to meet just 2 of the facility manager of these companies, so to face-to-face meetings. And just one of them was available to share data about energy consumption. We just told them to that we would have analyzed the energy consumption and show them some opportunity for waste heat recovery, and to for them was could have been an opportunity to improve their energy efficiency and their energy consumptions, but just one company was interested in that, and but we managed to perform the analysis anyway. So as I said, where no data were available, we used best available techniques reference documents, and environmental statements of similar companies in the area. So not all the companies are do this type of documents. So we get the information from the online. So the first activity I will show you is the COP Superstore, which is a shopping mall, for the quantification of potential waste thermal energy. This was the only case in which we have we managed to get real data of energy consumption. So the shopping mall, the COP Superstore, is covered 1,000 square meters area, and it's 1 kilometer far from the tower studied in the project. One thing we noticed was that there are closest tower to the shopping mall, and we considered that this fact in the end just for them to make a different scenario for the economic feasibility study. They gave us information about refrigeration units because the electricity consumption for the refrigeration of the cabinets within the supermarket was very important. So they have 2 refrigeration units, one called TN, which stays for normal temperature, because the cabinets must be kept between 0 and 4 Celsius degrees. The refrigeration unit called BT is low temperature, stays for low temperature, because the cabinets must be kept at minus 22 Celsius degrees because of, for example, meat or fish storing. Other information, so they shared with us data of the month of January 2018 and of August 2018. Because January and August are respectively the coldest, one cold month and one hot month, and so we asked them just two months of data instead of ask them 1 year of data, and the other values are have been obtained through interpolation, linear interpolation. Then they gave so the data they gave us were temperature and pressure of the gas at the evaporator and at the condenser of the refrigeration units, and then the electricity data, which includes the electricity consumption every 15 minutes. So the first thing we did was just looking at the data in order to get the standard operating condition. For example, we got that temperature at the evaporator must be kept stable independently for the external condition, and the operation hours are from 6 to 24 7 days a week. So all the year long the system is working. Then we got also some anomalies in the operating condition. For example, there was a week during between the 15th of August where the refrigeration unit couldn't cool down the gas at the condenser. probably because the external temperature was too high, probably because the dry cooler didn't work properly, probably because there were too many people in the shopping mall. We don't know this, but I mean, we detected this anomaly because yeah, the only data we got were the temperature and the electricity data. So we don't know this, but we just detected these anomalies. And then from the electricity consumption of the month of January and August, we with the linear interpolation, we detected the consumption of each month of the year, and then from the electricity consumption through the giving a value, plausible value to the energy efficiency ratio, we calculated the available waste heat, the heat rejected in the environment through at the condenser of the refrigeration units. So, for example, in this case, giving a value of 2 to the energy efficiency ratio, the total waste thermal energy amount to 2 gigawatt hour per year. Okay, then we detected also a supermarket in very close to the towers, 200 meters, but we had very few information from this activity. So we only know that the cooling, they have a very small refrigeration unit within the grocery, let's say the supermarket. The cooling capacity was 10 kilowatt and the electric power 5 kilowatt. So we assume that the operating hours were all the year long, 24/7. And then the waste heat was calculated in the same way as did in the previous case, just considering an energy efficiency ratio of 2 and calculated, and we calculated the waste heat, which amounts at 118 megawatt hours per year. So very small compared to the previous case. Then we consider the 2 winemakers in the area, Casa Girelli SPA and Cantina Sociale di Trento. They are both 1 kilometer far from the towers, but they gave us no data. They gave us no data, so we performed the calculation through literature review and some assumption. So from the best available techniques reference documents, and we detected that, and from other documents, we detected that almost 90% of the electricity consumption in a winemaker site is due to almost 90% of energy consumption are electricity consumption, and are from 50 to 70% due to fermentation process, because during this process the grape need to be cooled down through some cooled water. So this water then is going to be cooled down through cooling towers or refrigeration units. So that we consider these aspects. Then we consider that distribution of energy, electricity consumption during the year And you can notice that the highest consumption are in the months of from August to October, because in this period there is the grape collecting and the wine making process is in this period of the year. So the fermentation is in this period, but there is also a an electricity based consumption due to to cooling the store of the winemaker site. Then we detected that the specific electricity consumption referred to the production varies with the yearly production, and it is decreasing. Is decreasing when the yearly production increases. So you can see some values here. So the potential waste thermal energy has been calculated considering a value for the specific production detected from other wineries in the area, and detecting the surface of the wineries from Google Maps. So we detected the total yearly electricity consumption of both the wineries, and we also made some hypotheses about the distribution of this consumption through the year. So up to the 70% of the total electricity consumption is consumed for refrigeration, 20% all the year long, and fermentation processes from August to October. So this is the distribution we hypothesized. So the calculated waste heat is about 1,500 megawatt. Sorry, this is here is missing 1 megawatt hours per year, considering an energy efficiency ratio equal to 2, like the previous cases. This is instead fruit and vegetable transformation manufacturing, Trento Frutta. So it is 500 meters far from the towers. It's a big company producing semi-finished or finished product, fruit juice, let's say, fruit juice, and they sold them to other company in bottle or in different sizes of jars. So the total production is up to 70 million of jars, and but they didn't share any data, so we proceed with literature review. We discovered that in Europe, more than 50% of juice production is orange juice and apple juice. So we focus on this type of processes, so that we detected that more than 80% of the energy consumption are thermal, and the temperature are between 40 and 120 Celsius degrees, but this depends on the process. So thermal energy would be directly available for waste heat recovery, but we couldn't analyze. We couldn't take this into consideration for our analysis, because it's really processes depending, and we needed more detailed information. So we proceeded like in the previous case, and we basically calculated the electricity consumption through some reference values and making some assumption about the number of jars and the jar size distribution. So we detected the production, the amount of production, so 21 million of liters a year of fruit juice, and then applying again an energy efficiency ratio equal to 2, we detected that the waste available waste heat available could be 6 gigawatt hours in a year. So very high compared to even to the shopping mall, which was 2 gigawatt hours per year. Last case was leisure center, the swimming pool close to the towers, 450 meters, the surface of 450 square meters, but also in this case no data were available. So through the literature review, we detected that thermal energy is most relevant energy consumption, and through through good practices, one leisure center with swimming pool could save per year 763 kilowatt hour per square meters a year. So we consider that the good practice is one a leisure center can apply is for sure the waste heat from the water of the swimming pool recovery for preheat the heat of the swimming pool. But we consider that all this waste heat could be delivered to the district, our hypothetical district heating. So from this value we arrive to potential waste heat value, potential waste thermal energy value, so 189 megawatt hours per year. So very small contribution, also considering that a swimming pool could reuse it internally. So just to recap a little bit, these are the quantification of potential waste thermal energy. These are the activities on the left, and the waste thermal and the available waste thermal energy per year. So in less than 2 kilometers of radius area around the towers, there is an availability, a potential availability of 10 gigawatt hours per year. Very, very promising, but let's see how it is distributed, this energy along the year. And it can be noted that all the activities have more or less constant availability of waste heat. Only the winemakers have this peak of waste heat, waste thermal energy availability during the month of August, September, and October. On the right side of the slide, you can see instead the monthly thermal loads of a tower. Below zero, you can see the energy losses during to transmission losses, ventilation, infiltration losses. And so from this bar diagram, we can get the value of the distribution of heating demand load along the year. The red bars represent the heating demand, and so even in the worst cases, so in December and January, the heating demand is 50 megawatt hours per month. whereas the superstore, for example, just to have a comparison, the superstore in January and December can reject in the district heating network almost more than 150 megawatt hours. So there is more than a higher availability. So the monthly average is 12 megawatts per month of coming back to the thermal load of the tower, and the yearly heating demand is 360 megawatt hours per year. Compared to the waste heat availability is 1/3. So the waste heat availability from the SuperScope superstore could cover the heating demand of 3 towers. So our techno-economic feasibility study is based on the results of COP Superstore case, just because they gave us some real data, so we could really think about a real case. So the layout of the recovery system is is reported in this very simple scheme. We have 2 collectors, one hot and one cold, connected to the condensers of the 2 refrigeration units of the COP Superstore, and heat exchanger, then pipings going to other 2 collectors connected, one cold and one hot, connected to the heat generation station of the towers. On the right side of the slide, you can see a possible layout of the piping, a possible connection from the COP Superstore to the towers. And for the economic feasibility study, we needed to calculate the thermal losses, for calculate the energy, the useful thermal energy delivered to the towers, and then to calculate the savings of the towers in terms of euros, and the pressure drops in order to size the pumps and to calculate the pumping costs between the COP Superstore and the towers. So we made some hypotheses. We give some values to these parameters, some parameters important for the sizing and the calculation of pressure drops and thermal losses. So we considered a 195 kilowatt heat exchanger, and we assume that the system is working during the operating condition of the shopping mall, so between 6 and midnight, 6 a.m. and midnight. The water is available, and from at the Superstore, the water is available at 30 degrees Celsius degrees, and is returning back at 15 degrees. The temperature, the supply temperature to the tower's heat generation station depends on the thermal losses. So that we have considered two types of pipes in PEAD, which basically it's a type of plastic, let's say, and pre-insulated steel pipes. So there were differences in thermal losses, and so in the supply temperature to the towers. And then let's have a look to the economic figures. So in the case of pre-insulated steel case, pre-insulated steel piping, in that case, the investment costs are this distribution. Let's say we have pumping station the cost for pumping station includes the heat exchanger and the pumps and the collectors and so on, the valves, the piping, so in this case pre-insulated steel pipes, and the digging. So the digging is a very relevant voice, also because it has to be considered that this layout is not linear, and there is also a slope between the COP and the superstore, the shopping mall, and the towers. So it is a particular layout. So the digging is a relevant voice in any case, even in the PEAD pipe case. Just to give to give an example of distribution of investment costs. Then the operating costs are the electricity costs, the electricity consumption cost for pumping, and it has been assumed this value for electricity maybe should have been a little bit updated because this calculation was made more than 1 year ago, and the cost for buying waste heat from the superstore. So this system has been supposed to be owned from a third party, so external from COP Superstore and the towers. So this is the cost that the owner of this system is paying to the COP Superstore in order to convince them to give the waste heat to the district heating. So it has been paid 1 euro cents per kilowatt hour. Then the revenues of this system, of this investment, are derived from the waste heat sold to the towers. So it has been considered to 5 euro cents per kilowatt hours, which is more or less 50% of the natural gas costs, and it is a value that it is believed economical, sustainable economically, and considering also the performances of the heat pumps operating in the season. This is in this table, I summarized the economic figures of the investment of the economic feasibility study. I put 2 scenarios, or it's better to say 4 scenarios. One scenario is the towers considering a distance of 1 kilometer from the COP Superstore, and for each for this scenario 2 types of pipe. So the PID 100 is at the nominal diameter of the pipe, and the pre-insulated steel pipes. We can notice that the useful energy to the towers is changing, of course, for the energy losses, because when the pre-insulated steel is used, more energy is delivered to the towers, and the supply temperature is higher, 26 Celsius degrees. So the investment cost would be higher because the pre-insulated steel costs more than PID pipes, but the payback time would be 8 years compared to more than 25 years. Instead, considering another scenario which was not object of the study in Stardust, but we wanted to investigate also to the influence of the distance on the economic figures. So considering the towers closest to the COP Superstore, they were 400 meters far from the tower, from the COP Superstore. We have that the payback time is 3 years. In both cases, even with PAD pipes and with pre-insulated steel pipes. So the distance could positively influence the investment costs independently from the type of pipe that is used. So that's all from my side. These are the results, and I will let you give you space for questions.
Thank you very much, Rosanna, for that very complete and interesting presentation. As a non-expert myself, I found it really interesting to discover how much sort of waste heat is produced, and if we can actually capture that and reuse it in some way, it would solve a lot of problems, I think. Okay, thanks for that. So if any members of the audience would like to ask questions, you can use the chat and I can put the questions to Rosanna for that. We do have a question already in the chat, which are the energy costs considered for the payback time calculation? So in order to calculate payback time, what are the energy costs? I think you may have mentioned something like that just now, but perhaps you could elaborate on that. And the last part of the question was, what variability can be expected?
Okay, so the energy costs are the can you see
Yes.
the screen as well? Yeah, okay.
Yeah.
The electricity costs for basically for pumping the water from the heat exchanger connected to the COP Superstore, and to deliver it to the towers. This is one energy cost in order to make the system run, to make the water, to pump the water, and it has been considered 15 euro cents per kilowatt hour. And the other cost we have considered is the cost for buying waste and waste heat from the superstore. Because, as I said, it is supposed that this system is owned by a third party that can be the municipality, a local energy facility, I don't know. But we consider to give a value to the waste heat in order to like an incentive to the COP Superstore, in order to convince them to install this system, to give the waste heat and to reject the waste heat in the district heating network. These are the costs, and it has been considered to in order to be enough convincing, 1 euro cent per kilowatt hour of waste heat. I don't know if I replied to the.
Okay, thank you. Well, we do have another question. So can the process of obtaining or assessing the feasibility, the technical economic feasibility of the recovery systems, can that be automatically performed?
Yeah, this is an interesting question, because after this activity in this project, yeah, we analyzed other cities and other in other countries, And of course, we tried a way to automatize this process of at least quantify the waste heat potential in the area. So we have developed a QGIS tool in order to automatically calculate the waste heat using some energy specific consumption coefficients or relation, and this GIS tool can, from a list of companies, can calculate automatically the waste heat available in a well-defined area. So the answer is yes, it can be automatically yeah, the process can be automatized, let's say, but I mean, the results must be, in my opinion, validate. So if the tool can do a top-down analysis, let's say a top-down analysis where we can have the overall idea of the waste potential waste heat. A bottom-up analysis is needed to validate this the result of the tool. So the reply is yes, and yes and no, let's say.
Okay, thank you for that. Now, I don't know whether you can actually see the questions. We've got a couple of other questions coming. I'll read them out. Given the low temperature delivered to the towers, we have Raymond Bulter, who says that he assumes that there are heat pumps included in the design at the towers. And was this cost, so the CapEx and OpEx, was that cost included in the analysis?
No, that's a good point. It is considered that the waste heat delivered from the COP Superstore to the towers will be increased. The temperature of the water would be increased by using heat pumps. But we didn't consider the heat pumps in our calculation. Because it is supposed that the heat pumps are owned by the towers, let's say. So the system I have studied is just to connect the two, the COP Superstore and heat generate and the collectors of the heat generation station. I mean, the system and analyzed ends here.
Okay, thank you. Just continuing there in the sort of question box, we've got a comment and some questions from Anne Art, who is in Derry, which is one of the follower cities in the Stardust project. So she says, thank you, it's a very interesting presentation. She's saying that Derry Council is completing a feasibility study into a district heating system for Derry. We are considering taking waste heat from a biomass power station, but the distance to the anchor customer is a bit too far for an initial network. Also, the waste heat temperature is lower than we'd like. The temperatures that for Trento appear a lot lower than what we would require in Northern Ireland. Can I ask what temperature the waste heat is from the Superstore before it's boosted via any heat pump?
Okay,
that's the first question that Anne has there.
Yeah, maybe I was too fast here in this point. So the supply, you can see here the layout of the system, and this is the hot collector where the water from the condenser of the refrigeration units is collected here before going to the heat exchanger. Here the temperature is considered to be 30 degrees. Okay, yeah, 30 degrees is the starting point. Of course, the heat exchanger has some heat losses, like we consider 95% as the efficiency of the heat exchanger. And here at the delivery, at the hot collector close to the tower generation station, in the case of pre-insulated steel pipes, there is a temperature of 26 Celsius degrees. So this is the in the case of PAD, the water is delivered at 20 degrees. The heat losses are higher because of the distance and because of the material, of course. And so instead, in the other case, with as long as the distance is reduced, I mean, with the closest tower, of course, the thermal losses are lower, and the water could be delivered at even higher temperatures, so 24 Celsius degrees and 27 Celsius degrees. I don't know if I was if I replied to the question.
Okay, Anne can always come back if not, but she does have another question. She's talking about the sort of the cost of the waste heat to the towers. Is it lower than fossil fuel alternatives? Because she's saying that they cannot achieve this for district heating in the UK because gas and oil are lower in cost.
Okay. Yeah, of course, this value is considering the waste heat sold to the towers has been priced with 5 euro cents per kilowatt hours, which is more or less the 50% of the cost of natural gas that is actually so far is the sources for heating demand of the tower. So in order to be competitive with the to be competitive, it has been considered this this value for the waste to price the waste heat, and because 10 euro cents per kilowatt hour should be the natural gas cost in Italy. I don't know if this value is updated, but I mean, yeah, that's our value. That's our assumption.
Okay, thank you, Rossana. I think you know, we're coming to the end now. So thanks to you and to your colleagues at EURAC for that presentation. Just before we leave, I'd like to remind people that this webinar series continues, and next week we've got a couple of webinars, one on the Thursday at 11 o'clock, that's Central European time, on innovative business models and the lessons learnt, and that's in collaboration with the City Exchange project. And then on the following day, on the Friday of next week, we'll be talking about replication strategies and comparing those, and we'll have on board you know, lessons or comparisons with the smart city project called Positive. So we're sort of doing a joint webinar with them, and again, that's at 11 o'clock Central European time. So all this information will be on the Stardust website. And just a reminder for those who are unaware that the Stardust final event, so it's a physical event, will take place in Pamplona on the 28th and 29th of February. Again, there will be information about that on the website. So do follow the social media and the website. At the moment, we're quite active on there. There's a lot of sort of information, lots of news coming out on the social media at the moment. Things are moving fast. So thank you to the audience, and thank you again, Rossana. And hopefully we'll see everybody next week on the Thursday for the following webinar. Thank you.
Thank you. Bye.
Bye.